Hello, everybody. This is a video that will help you to decipher rate tables and to try to figure out the rate law for a reaction and to calculate K. So the first step is to look in your rate table and find the row that has the lowest concentrations. And so for this particular rate table, it has to do with the reaction of pH3 and Cl2. So we have the reactants pH3 and Cl2 in the first two columns. And so what we're going to find is the row that has the lowest concentrations, and that's row 2. You can see that these are lowest. So what we'll do next is find another row where just one concentration changes. And so we're looking for a row that has one value that's the same as this, and one concentration is changing, and you can see that's row 3. So what we're going to do is compare row 2 and row 3, and we're going to ask ourselves two questions. So the first question is, by what factor does the concentration change? And then we're going to ask ourselves, by what factor does the rate change for the same two rows? So in this particular case, when we compare row 2 and row 3, the way we figure out the factor by which the concentration changes, I'm going to call that the concentration factor for pH3, and I'm going to just call it the CF. All right, so the pH3 CF is simply going to be the higher concentration for those two rows, 0.41, over the lower concentration for those two rows, 0.12. And when you do that math, you end up with a concentration factor for pH3 of 3.42. In other words, to decipher what this means, this 3.42, it means that when we went from row 2 to row 3 experiment, the concentration of pH3 increased by a factor of 3.42. So now what we're going to do next is figure out the rate factor for the same two rows. And I'll call that the rate factor, RF. So the rate factor, we do the very same thing. We take the higher concentration, that's the second of the two rows, and we divide it by the lower concentration. And when we do that math, we end up with the number 11.7. Okay, so we have three possibilities from this information. This is the information that's going to give us the order with respect to pH3. So we're asking ourselves, based on the 3.42 concentration factor change and the 11.7 rate factor change, is the order with respect to pH3 zero order, first order, or second order? So here's how we think about it. If zero order, the rate will not change. And so what we see is, in fact, the rate does change. So it can't be zero order. Then we ask ourselves, if first order, the rate, well, let's just say it this way. The concentration factor will equal the rate factor. In other words, our concentration factor is 3.42, and if it were first order, the rate factor would be 3.42. So since that's not true, it's not first order either. If it's second order, the concentration factor squared will equal the rate factor. All right, so if that's true, then we have to find out what is 3.42 squared, and we have to see if that's equal to 11.7. And when we do the math with the number 3.42 squared, sure enough, we get 11.7. So our conclusion as a result of this little test that we did for pH 3 in comparing the second row to the third row and seeing that the concentration of pH 3 is increasing and the rate is increasing, what we discovered was that the reaction is second order with respect to pH 3. Okay, so with that in mind, then we can do our second test. So I'm just going to take a little bit of erasing time here. And we'll remember that it's second order with respect to pH 3 in a little while here. Okay, the next thing that we do is we want to try to figure out the order with respect to the other reactant, Cl2. So now we're going to find a situation where pH 3 is staying the same and Cl2 is changing. And I see that in the comparison of reaction 3 with reaction 1, pH 3 is staying the same. And when we think about reaction 3 going to reaction 1, we see that the concentration of chlorine is increasing. So what we're going to try to do is figure out the concentration factor for chlorine, and that's going to simply equal the higher concentration in experiment 1 divided by the lower concentration in experiment 3. So when we take 0.66 over 0.25, we get the number 2.64. So there's our concentration factor for Cl2. All right, then we do the rate factor for those same two rows. And so we're thinking about, again, the rate in experiment 1 over the rate in experiment 3. So 1.6 times 10 to the fourth, 6.07 times 10 to the third. We do the math, and lo and behold, we get 2.64. So thinking about our conclusions carefully, if it were zero order, then as the concentration changed, the rate would have stayed the same. So is it zero order? No. If it's first order with respect to Cl2, then the rate factor and the concentration factor for Cl2 would be equal. And in fact, they are. So now we know it's first order in Cl2. And we already knew that it was second order in pH 3. And with that information, we can now do part A, which is to write the rate law. And the rate law is always given in the form of the rate equals a rate constant times the concentration of each reactant. And in this case, we have rate equals the rate constant times the concentration of pH 3. And we go over here and we see that it's second order in pH 3, so we write a 2 as an exponent. And for Cl2, it's first order, so we just leave that because that's automatically first order. And there's our answer to part A, find the rate law. All right, if we have the rate law, then we can calculate the numerical value for K. And there are going to be two really important pieces in that. And the first piece is to recognize that overall, the order is 3. We have second order pH 3 and first order Cl2. And because the overall order is 3, the K units, as we discussed in class, are going to be molarity to the -2, seconds to the -1. So we're going to keep these units in our mind as we calculate the numerical value for K. So to find the value for K, we can choose any one of our 3 rows. Just choose one row, and I just decided for random reasons to choose row number 1. And we're going to plug in our value for the rate, 1.6 times 10 to the fourth moles per liter per second. The value for pH 3, 0.41 molar and square it, and the value for Cl2, 0.66 molar, and we'll not square that. We'll keep that to the first power. Okay, so what we end up with is 1.6 times 10 to the fourth moles per liter per second. And that equals our unknown rate constant times 0.41 molar squared times 0.66 molar. And you do a little bit of algebra on that. 1.6 times 10 to the fourth moles per liter per second divided by 0.41 molar squared and 0.66 molar. We end up getting a value for K. And the numerical units for K are going to be the ones that we talked about there. And you can probably see that as you look at the algebra. But the value that we get for K is 1.4 times 10 to the fifth moles per liter to the minus 2 seconds to the minus 1. Finally, we can calculate a new rate under these different conditions, 0.33 molar pH3 and 0.52 molar Cl2. Those are some values that aren't in the table. We can calculate the rate now that we know the concentrations and we know the rate constant. We just plug in the rate constant, we plug in these new concentrations, and we get the rate. So our rate in part C is going to be 1.4 times 10 to the fifth and then we've got our 0.33 molar squared and our 0.52 molar Cl2, and we do the calculation, and the value that I calculated was 7.9 times 10 to the third, and the units for rates are always moles per liter per second. All right, here's another problem. Once again, we've got 3 rows of concentration and rate data. We want to find the rate law, calculate K, and then we want to calculate the rate under these different conditions. So like we said in the first example, what we're looking for is the row that has the lowest concentrations, and then another row where only one concentration is changing. So I'm in sort of inspecting here, and it looks like row number 1 has the lowest concentrations of F2 and O2. And now I'm looking for another row where only one of those 2 values is changing, and it looks like in row 3, O2 is staying the same and F2 is changing. So I'm going to compare 1 with 3. And I'm going to look at my concentration factor for F2. So my concentration factor for F2 is going to be my bigger number divided by my smaller number. And when I do the math, I get 1.53. Okay, now I'm going to go over to the rate for row 1 versus row 3 and see how the rate is responding. 0.83 and 0.83. So when I evaluate that, my rate factor is 1. In other words, the rate is not changing. And I immediately recognize that when a concentration changes, but the rate doesn't respond, the reaction must be 0 order in that reactant that was changing. So when F2 changes, nothing happens to the rate. So my conclusion is 0 order in F2. All right, now I'm going to look for another set of rows where one of the concentrations is staying the same and one is changing. So I went from row 1 to row 3. Now I'm going to go from row 3 to row 2, and I can see that F2 is staying the same, but O2 is increasing. And we're looking for the concentration factor for O2. And so as I go from row 3 to row 2, I see that my concentration of O2 goes from 0.71 to 1.1, so bigger on top, smaller on the bottom, and I get the value 1.55. And when I look at my rate factor for experiment 3 and experiment 2, I put my 1.99 on top, 0.83 on the bottom, calculate my value, and I get 2.4. So my possibilities for the oxygen order are 0 order, and if it were 0 order, the rate factor would be 1 and not changing, so it's not 0 order. If it were first order, then my concentration factor for O2 and my rate factor for O2 would be the same, and they're not. So surely it's second order, but we can confirm that if we simply take 1.55 squared. And so we're going to ask ourselves the question, 1.55 squared, is that equal to 2.4? And we do the math and we find out that it is. And as a result, what we know is that the reaction is second order in O2. And as a result of all this stuff, we can write the rate law. And so our rate law is going to be 0 order in F2. So we literally don't write anything about F2. And second order in O2. And there's a reaction that would be 0 order in F2 and second order in O2. Answer to our first question, find the rate law. Now we can calculate K by simply plugging in the value for the rate and the value for the O2 concentration from any of our rows up here in the table. And so once again, I'm just going to choose row 1 for the fun of it. And so my rate from row 1 is 0.83 moles per liter per second. And my oxygen concentration from row 1 is 0.71. And it gets squared. And importantly, I should probably note that I'm expecting for the units for K. If a reaction is overall second order, the K units are molarity to the -1, seconds to the -1. So if I do the algebra here and calculate my K, the value that I end up getting is 1.6 times, not times anything, is literally 1.6. And the units then for my K, we said, are molarity to the -1, seconds to the -1. All right, finally, now we've got a K, and we have some new concentrations in question C up here. So I'm going to erase a little bit, and knowing what our value is for K and knowing our overall rate law, we can find the rate under those new conditions. So we want to know what the rate is, and we have our rate law. So we plug in a value for K, and that value that we had just previously calculated was 1.6. And then we plug in our value for O2, which is 0.88. And we square it. And then we do the calculation and we end up with our rate. And in this particular case, our rate is 1.2 moles per liter per second. So those are two examples of how you disentangle the information in a rate table. And for your note taking, what you might do is take a screenshot of this very first page, which then goes over all the steps. And I'll just say them real quick again. Doing a rate table, what we're going to do is, first of all, find the row that has the lowest concentrations and another row where just one concentration is increasing. Second thing we do after we do the finding of those things is find the concentration factor for that particular reactant whose concentration is changing. Larger over smaller gives us that value. Then we find the rate factor for the same two rows, and we're looking at the rate of the larger concentration divided by the rate for when we had smaller concentration. So we get our concentration factor and rate factor. Remember that there's only going to be three possibilities. So first possibility is the concentration is changing, but the rate isn't changing at all. It's zero order. If the concentration factor and the rate factor are the same, it's first order. And lastly, if the concentration factor squared is the rate factor, it's second order. Hope you enjoyed the video, and if you have any questions, don't ever hesitate to come to office hours.